I actually took a vow of seriousness. I'm not allowed to tell any jokes. It's part of the CaN+2015. Is that what it's called? To rid myself of all emotions. It's the like the Vulcans, but it's okay. So I don't want to. Before we start, since I have all this extra time, I want you all to join GSoft. So here you go. Kent State, are you out there? There are only 18 members of GSoft from your entire campus. 18, all right? University of Pennsylvania, we have 44, okay? So what's going on, right? It's free for students. Just sign up. Go now. Sign up. Once we become a bigger, we can get all sorts of extra stuff. And I'd like to say something that I usually don't say anywhere else. If you don't support GSoft, there's no place for liquid crystals at the APS. All right? We are the home for liquid crystals. All right? We're the ones that's going to support the liquid crystal sessions. All right? Okay. So now I'll start. I want to tell you about cholesterics. And there's a larger program, which is, what's the difference between cholesterics and smectics and biaxial nematics? And I know there's all these chemistry reasons. There will be no chemistry in this talk, so everybody can relax, right? There's going to be only math. I'm sorry, okay? Okay, so only math. And I'm going to tell you about the various kinds of things that cholesterics do. So why would I even think that a cholesteric, why would I even want to talk about at the same time biaxial nematics, cholesterics, and smectics? Because when you think about them from the point of view of symmetry, you kind of think they're not that different. After all, a smectic has this periodic ground state. So does a cholesteric, right? At least every picture you've ever seen of a cholesteric, you always see the fingerprint patterns, right? The last talk, oh, it's a fingerprint pattern. Obviously, it's a cholesteric, right? So they have stripes also. You might think that smectics and cholesterics would be related to each other somehow. And certainly, when you write down the free energy of excitations, when you talk about models for focal conic domains, you treat them identically. But then you think about the cholesteric, and something that Peter talked about. Peter's always wearing dark green, so he camouflages in with his van, right? Okay. The first time I met you, you were wearing a dark green blazer, right? I do. It was in Pullman, Washington. Okay, so you look at the cholesteric, and the cholesteric, well, there's this molecular axis, and there's the pitch axis. So there's the cholesteric axis, the molecule, and the pitch, which is perpendicular to it. And you can take their cross product, and you get this other direction. And so you have a triad. Everywhere in space, there's actually a frame, 3 directions that are different from each other. We call it N and P and not N. Okay? We could call it not P, but we didn't. Okay, because we think the pitch is important. So then you say, oh, that's just like a biaxial nematic. A biaxial nematic is a situation where you have something with a symmetry of an eraser or brick, where you have molecules that are, instead of being uniaxial, or biaxial, and they have a shape. And those truly have biaxial order. And everywhere in space, you have orientation of a whole frame. So you might think, oh, a cholesteric and a biaxial nematic, they're kind of similar, right? Can I describe the biaxial nematic and the cholesteric all together? And you might also think I could describe the smectic and the cholesteric together, because they both have stripes. So is a smectic, can I describe a smectic with a biaxial nematic? Is the algebra, or is the structure of topological defects in the biaxial nematic different or the same as the defects in a smectic? I don't know. So that's what we wanted to figure out. You can see that there are some discrete things that are different. There are discrete translations that are different in the different phases. In particular, a smectic has this period, you have to shift it up by 1 layer spacing. A cholesteric, you don't have to. A cholesteric, you can shift it up by anything you want as long as you do a rotation around the z-axis, right? So a smectic is actually rotationally symmetric around the z-axis. There is no screw axis, but a cholesteric is different. A biaxial nematic has different symmetries also than the cholesteric. So are the discrete symmetries enough to mess everything up, that these are all very different phases? Or are they all the same phase? So everybody knows that if you have what's that called, a paper with a question as a title, the answer is no, right? But there's no question yet. So let's start with the Smectic. Here's a picture of the Smectic. You can either think of it as some neat thermotropic system or a bilayer system. I don't really care. You know, the thing about free energies, I can write down any free energy. You give me a texture, we can always find some free energy that it minimizes. That's not the trick. The trick is to look at this, to see something really complicated that Michi makes, right? Michi made this picture, and you say, what's that? Can I understand that? I mean, that's not neatly ordered, right? That's nothing like this, right? This is what theorists do. Theorists talk about, oh, let's take the system and let's make it flow. But let's make it flow so slowly that it always looks like that, right? And it never gets messed up, and it always flows. And if you didn't flow it slowly enough, if it doesn't agree with Oleg's experiments, it's because he didn't do it slowly enough. He was impatient, okay? And so that's what we do. So we just, I want to try to study things that are about the symmetries of this picture and the topology of the picture, which is much more resilient to dynamics. So let me tell you something about Smectics, which is a little weird. See, it's lovely to speak here because I know I can say that, and I know what everybody knows what I mean by weird, right? Everybody knows what weird means. So the thing about a Smectic is Smectics have disclinations, right? So you can imagine here are the layers of a Smectic. They're wrapped around like a Sunday paper. Are graduate students here? Yeah? It used to be on Sundays, you'd get this newspaper. It was this huge paper thing. In fact, in New York City, it was so big that you got half of it on Saturday, right? It wasn't news. It was the old part. It was, you know, the fashion section, right? And, you know, wasn't it fashion section, the science section, you know, things like that. You get half on Saturday and you get the other half on Sunday. So this would be like a paper folded over, and here's the insert. Here's Parade magazine, okay, squished in there. Or you can have it nice and layered, or you can have a disclination like that. So I don't mean a dislocation, I mean a disclination. I mean a situation where the layer normal changes. Here it rotates around by minus pi. Why did I say minus pi? Because I go around counterclockwise, and it goes around clockwise. Here, if I go around counterclockwise, it goes around 2 pi counterclockwise, right? And so forth. Here, if I go around counterclockwise, it goes around pi counterclockwise. It goes the same direction I'm going. And I can have a +1. Now, we all know, you look at the cover of, you know, most liquid crystal texts, you look at pictures here, you look at this picture, right? When you look at nematics, and you look at a Schlieren texture in a nematic, you have these things. Here's a +1 defect because there's 4 brushes, right? This is under cross polarizers. Why do you get 4 brushes? Because it goes through the polarizer direction twice and the analyzer direction twice. So it goes around 2 pi. Sometimes it can go around just pi, and you have 2 defects, 2 brushes ending on a defect. But we know and we learn, and it's like a lovely thing, that the defects just add. You can take 2 +1 defects and make a +2 defect. You can take 2 +2 defects and make a +4. You can have a +2 and a -2, and they add up to 0. Because when you're all done, it's just about counting the number of brushes that come out. But Ponaru proved a real theorem, right? I found this out. Mathematicians, when they write papers, they're always correct, right? It takes many months to get their papers published, but they're checked. Somebody else actually reads the paper, right? And so maybe 2 people, right? And then you respond. And then when you respond, you actually can't just say, we added the reference that you wanted, right? They want like a more substantive response, right? Very, very hard. It's very, very honest subject. So Ponaru proved that you could have any kind of minus defect you want. So you can have -3/2, -1, -1/2, 0. But you can't have +2. You can't have +3/2. There's no way to take 2 +1s and merge them together and make a +2. And you wonder, isn't that weird? Because you can do it in a nematic, right? In a nematic you can do it. Why can't you do it in a Smectic? Right? Isn't that weird? Do you think it's weird, Dave? Because you think you can add them together. Not only that, right, for you math people, right? If you believe that homotopy theory, which tells you the charge of these things, is correct, that means that it should be possible to take two group elements that are +1 and multiply them together and get a +2. And apparently, Ponaro says you can't do that. But you can subtract. You can't add. So this confused us for a long time. I mean, it didn't confuse us. It was a theorem. We could read the theorem. We could reproduce every step, but we didn't understand what it was. But then we thought of this very simple model. Right? Here is a smectic. And where's the smectic? The smectic lives in the xy plane. Okay. And what I'm going to do is I'm going to take level sets of some function phi. So in other words, phi equals 0, that's one of the layers. And phi equals 1, that's the next layer. And phi equals 2, that's the next layer. See how clever this is? Because by doing that, they never intersect. Phi equals 1 and phi equals 2 can never come together if I have a smooth field, because there can't be 2 points that, one point that has 2 values of phi. But what I'm going to do is, instead of looking at level sets of phi in the plane, you know, it would be like, what's that called? Equipotentials. I could be doing equipotentials in the xy plane. Instead, I'm just going to draw phi of xy like it's a surface. This surface is not the smectic. Everyone get it? The smectic lives in the white plane. Okay? This is just a surface. This is phi of xy. But level sets, of course, it's not some word that was invented, you know, 1,000 years ago for no reason. It makes perfect sense. It's this level set. You intersect the surface with phi equals 0, and that intersection is the level set phi equals 0. And I project it, and then I can do it again for 1 and for 2, and there are all the layers. Okay, so you see the layers are just the cuts. And of course, I'm from the Midwest, so driving here from Akron, it was just great, okay? You feel really claustrophobic when there are mountains. Like, you know, I could just keep seeing, and like it was just totally relaxing, right? I realize being in a big city or being where there are mountains makes me nervous, right? Unless you're on the top of the mountain, right? There's always something, you know. Maybe that's why people always want to get to the tops of the mountains in Colorado, right? Because they really want to be in the Midwest, right? They want to be able to see everything. But in places other than the Midwest, there are these maps called topographical maps. And you realize that the smectic layers are just the isocontours on a topographical map. So here's Mount Rainier. And Mount Rainier, you have these lines. And of course, the lines, every topographical map is a smectic, because the lines can't intersect. 1,000 feet and 2,000 feet can't be the same, right? Try that in metric. It's really gross. 337 meters. Can't be the same as 679 meters. It's clear that feet is the better unit for it. So what do you see about the map? How do you know if you're at the top? Anybody? You have a ring because every way you look is down, right? So look, if that were in the smectic, that would be a disclination of charge 1. Because there's a ring, there's a circle, like right here, right? And so when you go around and you follow the normal to that line, the downhill direction rotates around by 2 pi. And it does here at point success, and it does that at Liberty Cap. And the truth is, if I didn't have numbers on here, you wouldn't know the difference between a basin and a mountain peak. Basins and mountain peaks look exactly the same on a contour, on a topographical map, and they do on a smectic also. But what's special about the 2 peaks? Anybody know? Anybody ever climbed a mountain? Yeah, you've climbed a mountain, and you go to the top. So when you want to go from here to here, you go over this way?
Only if you want to be a glutton.
Right. You go through the pass. And there's a theorem, it's a real theorem, and it's even called the mountain pass theorem, so it's really easy to remember, that says between every 2 mountains there's a mountain pass. Come on, there's a theorem that says that every closed curve has an inside and an outside, okay? And that's also an important theorem, all right? But what does it mean for us? You see what a pass is? A pass is a -1 disclination, right? Because if I go around counterclockwise, the direction rotates around clockwise. So a pass is a -1 disclination. Uh-oh. If I try to bring 2 mountains together, The mountain pass theorem tells me there's always a mountain pass. I can't make the mountain pass disappear. If I bring the two mountains on top of each other, I have to eat the mountain pass with it. Right? So you think about it. They do this in Los Angeles. They have two mountains and they just cut the tops off. And now it's one mountain, right? Because they've cut it through the pass, right? Where I grew up, they probably have them in all the states. Mount Trashmore? No? You know Mount Trashmore? You do? Yeah. Okay. Right? It's in Indiana, right? The one I know is in Maine, Indiana. It's a mountain made out of trash, right? And then they, put snow on top of it. Okay. So you could do the same thing. You could take two mountains and you could fill in the pass with trash, right? Dave's like shaking his head at me. I mean, the entire city of Chicago is built on landfill, all right? It's the same thing, right? Okay, landfill is just underwater trash, right? And so you can make a mountain. But the point is you can't have a +2 because you can't put a mountain on top of another mountain. You always have to pull this pass in with you. And that's because smectics are funny. They're not just directions. There's this layering. And the layering is really important. And the layering is what prevents you from having something that has a +2 defect. Okay. So here's the cholesteric. Now you see every picture you ever see of a cholesteric either looks like this or doesn't look like this, right? And what I mean is often you see it, you say, oh, it's stripes, right? Or if it's not stripes, it's some green mess that's refracting light, okay? But you always see it, so your belief is that you're always seeing stripes or you're seeing layers perpendicular to yourself, right? But that's just the pictures we show, okay? Let's think about it. So here's a cholesteric. A cholesteric, you say, has a pitch. It rotates around. It goes around. You can draw these layers. The layers are just for fun. They're not really layers. They're places where all the molecules are pointing a certain way. That's the ground state. But suppose I give you some not ground state. Yeah, the ground state of a cholesteric looks just like the ground state of a smectic. All right? But now suppose I give you something that isn't a smectic. It doesn't have periodicity in density, but I just give you some molecules in space. When it looks like this, you know which way the pitch axis goes, right? But how do you know which way the pitch axis goes when it doesn't look like this? Right? And this was our quandary. In order to even talk about, remember, smectics are like cholesterics are like biaxial nematics. We understand biaxial nematics completely. We want to understand smectics. So we're trying to go from one to the other. Okay? So are smectics and cholesterics the same? How would I get the pitch axis? How would I get the triad? So here's my triad. Like I said, there's the pitch axis, there's n, and not n. But I haven't told you how to define the pitch axis. The only object there that's already defined is n. Okay? So what's the pitch axis? We say, oh, first of all, we want to take the pitch axis to be perpendicular to n, just like we do in the ground state. We take not n to be n cross p, so it's an orthonormal triad. And now we say the following thing. When you take the derivative of the director along the pitch axis, it rotates into the not n axis. It doesn't rotate into the pitch axis. It's a unit vector, so it can't rotate into itself, so it has to rotate into the not n direction. And this is how we're going to define the pitch axis. The pitch axis is defined this way, and q is the pitch. But of course, you can see I can multiply both sides by p, and I can get an equation here, which looks, I don't know, a little weird. But actually, if you look at it, it's an eigenvalue problem. There's p on both sides. So there's some matrix acting on the vector p that is entirely determined by the texture n. So you give me the texture in space. Somebody clever gives me the data. And then I can actually find this. There's a tensor, Cij, and this is the matrix equation. Right? And if you like indices, it's that thing on the bottom. Right? There's the tensor. And you say, oh, we're done, because now I can find the pitch axis. Hold on. But I'll remind you something that's a little funny about the pitch axis in comparison to the biaxial direction. All right? So you remember what's special about biaxial nematics? Anyone? Do you remember biaxial nematics? Biaxial nematics, Dave, what's special about them? Okay, well, there's only one property I want. Remember, in a uniaxial nematic, here's a minus 1/2 disinclination. Here's a plus 1/2 disinclination. I feel bad, always in the bright room side of the room. Minus 1/2, plus 1/2. Of course, I can do a rotation, and I can turn the minus 1/2 into a plus 1/2. They're the same defect. There's no such thing as minus 1/2 and plus 1/2. There's just a defect or there isn't a defect. It's an important feature about uniaxial nematics. But that same trick fails in the biaxial case. In a biaxial nematic, minus 1/2 and plus 1/2, I can try rotating them, but there's something bad's going to happen. When I rotate them, I have to rotate this guy. The only way I can say they're the same is if I can rotate one to the other while holding one of them fixed. Right? In the uniaxial case, if I can get to it, there, I can hold this guy fixed. I hold this one guy in the corner fixed. This guy here. Right? I'm just rotating around its center, but it's symmetric, so you can't tell. But in the biaxial nematic, I'm forced to rotate it. And this is an important mathematical thing that when you do these homotopies and decide if two things are equivalent, you have to hold one thing fixed. So they're different. So what's weird about that when I talk about the cholesteric? You see, a cholesteric, the pitch axis is not some internal thing like the orientation of the eraser head. The pitch axis is coming from derivatives of the director field. It knows about space. See this thing here that I did? This transformation did not, flipping the rods around, flipping the erasers around had nothing whatsoever to do with rotating space. But in a cholesteric, the pitch and the director talk to each other. The pitch knows about the orientation in space because it has derivatives in it. Right? And you know, this is the most important thing, is that a biaxial nematic can't escape. If a cholesteric were a biaxial nematic, I'd be able to do this, right? In other words, all the magic of the biaxial nematic comes from the ability to turn, say, a defect where the rods are all pointing like this. I don't know how to do this. Okay, here. Let's see. We'll use my head as one direction, okay? So it could be that as we go around, it's always like this on the boundary. But if I go into the center, where it starts going like this, then my head has to have a problem, right? My head has to have a 2 pi rotation in it. And it's that conversion of one kind of rotation, rotation around my torso to rotation around my neck, that is what biaxial nematics do. It's how they can transform from one defect into another. It's how all their magic happens. All the magic of the topology of the biaxial nematic happens because of this. Does a cholesteric do that? If a cholesteric is a biaxial nematic, it has to do that. So let's calculate the pitch. You can calculate the pitch. You can calculate polynomials if you like. It turns out that this matrix, what's wrong with this matrix? Any mathematicians here? What's wrong with this matrix? There's too many indices. It's not symmetric. So not being symmetric, right? It's not symmetric on I and j. It means that I'm not assured that I have real eigenvalues. I'm not assured that I have 2 eigenvectors, right? And they're not orthogonal either. So unfortunately, it's not a symmetric matrix, but I can check this condition here is the condition that the eigenvalues are real, right? And you know, it's some gross condition. It's not so gross. If I look at it, it's n dot curl n squared minus the saddle splay. Has to be greater than or equal to 0. Now I have an admission to make of my own ignorance that 1,000 years ago, it was 1998, okay? 1998, in the last millennium, I was talking to Yves Boulogan, who told me, he wrote this inequality down on a piece of paper. And he said, a friend of mine has told me that when this inequality is true, satisfied, there's a pitch axis. And I looked at him, and I had no idea. Okay, right? He said, do you know why? I said, no, I don't know why. He said, but this guy told me. I don't know who the guy was. Right? I don't know who told him, right? It could have been Ponaru, who lived down the street. I don't know, okay? Anyhow, I want to give credit where credit's due, right? When we realized this, I said, oh yeah, I remember him showing me this, but not understanding it. Okay, but you know, it's very difficult to cite somebody that way in Physical Review E, for instance. Right? How do you cite somebody who has passed on, right, for some comment they made on a piece of paper, right? It wasn't personal, but it wasn't his. You see, the problem was I can't credit it to him. This is something he told me that somebody else did, but I don't know who. Okay. So where were we? So you can find a pitch axis. I want to go back, right? You can find a pitch axis. You have some complicated problem to solve, but you can find it. And when this is positive, you can find a pitch axis and you have a pitch eigenvalue, and that's great. And we've checked that most of the time this inequality is true when you give me an arbitrary texture. But I'll show you where it breaks down. When this is not satisfied, when this is negative, it's not a cholesteric because there's no pitch axis. So you have some mathematical definition of when is it a cholesteric there. If you want, you could call that the cholesteric order parameter, right? We call it the cholestericity, right? To go along with diasteromicity, okay, right. Okay, so it turns out that if you think of the pitch axis and the n and the not n, that triad, it turns out it's actually much more, there's much more power, it is much more constrained than we thought it was. So some of you might remember the Frene-Serre apparatus that tells you about closed curves in space or open curves in space. Curves in space, where you have a vector, you have a curve, you have its tangent vector, you have the normal, which is the derivative of the tangent vector, and the binormal, which is its cross product. And there's this whole beautiful formula and formulation where the time derivative, or the derivative along the curve of this triad is just a rotation of the triad before, and its parameter is by two constants, the curvature and the torsion. Okay, and so a curve that's in flat space, a curve in 2 dimensions has no torsion. A helix has constant curvature and constant torsion. But it turns out, so remember P and N, the pitch axis and the director, they're orthogonal. This is the definition of not N and the definition of P, right? P, when you take the derivative of N along P, you get Q times not N. And then you can do something really gross. You can multiply by a very complicated set of things. You can multiply this equation by P, use a vector identity, and you actually discover that this is true. And you might say, so what? It turns out that putting that all together, you discover that this triad, P, N, and not N, is actually a Frene-Serre frame. And you take the derivative along the pitch axis, and you get two numbers. And you get the curvature, which is the curvature of the pitch axis, and you get the torsion, and the torsion is exactly the cholesteric pitch. So this is an amazing fact that if you agree with all my definitions of what the pitch axis is, then the pitch axis informs me, when I watch the pitch axis move through space, I start following the pitch axis, that the curve it traces out actually contains all this information in it. It contains the cholesteric pitch. Weird. So these guys did everything, okay? Let me show you a new picture. I'll show you. These guys did this. I'll show you a modern version of this. This picture is actually the picture that shows you that a cholesteric is not a biaxial nematic, though they didn't say that in the caption, right? But they drew the picture. So imagine we have this cholesteric, like so. So here's my cholesteric. And I'm going along, and here is a pitch streamline, right? The pitch goes along this curve, so I have the pitch along here. I can calculate the twist by integrating Q along here. The torsion, I just integrate the torsion as I go along this curve. That'll tell me how much the molecules have twisted. Okay, so you have some pitch axis. You follow it along, and everywhere in space, then you can say, oh, I'm going to put a direction of the molecule. Well, here's the weird thing. Imagine that I want to go from a texture where the cholesteric pitch is vertical in the center to the cholesteric pitch being radial at infinity. Does that seem familiar to you? Have you ever seen that texture before? Picking on you because you're right in front. Next time, don't sit in front. Right? You didn't see it? Remember I did this thing with my head and my arm? Right? So I was saying, can I go from a situation where the pitch axis, my arm, is radial out here, and the director must be perpendicular, to one where in the center, where the pitch axis is like this, and the director is rotating around, because it's a cholesteric. That's all it is. You see, this is the escaped biaxial texture, but in a cholesteric. Okay? But the cholesteric has layers. I just showed you I could sort of build up layers. I could build up this phase field. I could integrate along the pitch axis and get a phase field, right? So then you say, oh, phase fields can't be arbitrarily complicated. I already showed you that. I showed you why you can't have two mountains come together and make a double mountain, because they pull a defect in with them. Well, it turns out you can do this any way you like, but you can convince yourself that if you have lines like this and lines like this, and you can't have an infinite number of lines squished into a finite space, then you always have to have defects in order to go from this texture to this texture. Suppose I didn't have a defect. Suppose that they all just kept going up. Well, if they all kept going up, then there'd be an infinite number of these guys going up and being squished in this small space. So there has to be the last one that goes up. And then there's going to be a defect where it switches from going up to going down. Okay? So in fact, you can't do this. A cholesteric cannot have an escape biaxial texture without adding extra defects. All right, but then the game's off. Yeah, I mean, I could cut a hole in the Smectic, in the cholesteric also if I wanted to. So without any extra defects, I can't go smoothly from the, we call it the lambda texture, the pitch axis being pointing out, to the pitch axis pointing up. So unfortunately, a cholesteric and a biaxial nematic are different. I don't know, unfortunately. What's fortunate about it, or unfortunate is I can't now take all the machinery of the biaxial nematic and translate it into the cholesteric. Right? And people have understood this. This is a very concrete way of showing why that's true. And it's arising from the Smectic-like nature of the cholesteric, that has layers of some kind. So then you think, oh, well, that's good. It has layers. Here's another picture of it. Here are the defects. You know where this picture is? This is gray and black. Black is where the cholestericity vanishes, right? Black is where there's no pitch axis. That's a defect. When there's no pitch axis, it's because you can't define it there. So we have this situation where we have, this is a different picture of it, but you think to yourself, well, that's great. I just showed you that a cholesteric is not a biaxial nematic because it's like a smectic. Maybe it's a smectic, okay? You see this picture here? You ever seen this data? I want you to look at this, right? I want you to think about the implications of what I told you about the Frenet-Serre frame. So the twist, in order to have twist, the pitch axis has to be helical. It has to have torsion. If you figure out what that means, you can say whenever you have straight, nice straight pitch axes like this, right? There you can have whatever torsion you like because they're straight lines. But if you want to switch from one direction to the other, it's going to have to do it on a cusp. There's no other way to do it. It's going to have to do it discontinuously. Do you think there's a cusp there? Does anybody think that? We looked at it. We stared at it. See, you look at this picture, not this picture, right? See this picture? This picture always amazed me. Is this from your book, Peter? I think it's from your book. Yeah, I'm pretty sure. It's from somebody's book, okay? So this is a cholesteric under cross polarizers, and you see the stripes. And you see the stripes, and here's a whole domain where it just, unfortunately, it just happens to align with the cross polarizer, so it's black everywhere. But you notice how it doesn't go smoothly from one domain to the other? There really are diamonds there. It jumps. There's a cusp. It doesn't go, it's not that the pitch axis rotates smoothly, right? The pitch axis jumps. And we looked at this picture, not this picture, this picture, and we stared at it a long time and we decided there is a cusp, right? But you can decide too, right? We decided out here it's completely flat. It's a very soft cusp. No, what we're saying is if you look at where, forget about near the defect, all right? Away from the defect, is the crossover a short, sharp region where it goes, where it does the bending, or is it a hard region, or is it a stretched out region? Okay, I got out of order. So you say, oh, so maybe a smectic, a cholesteric is a smectic, but here I can now try to make the smectic layers again. See, we can make the smectic layers, build up the phase field of the smectic. Is a cholesteric a smectic? No. Because this is a smectic, this is a screw dislocation in a smectic, okay? And if this is supposed to, if the normal to this is supposed to be a pitch axis, these are supposed to be the levels, the directions. The pitch axis are these helices that go very softly around here. In the middle, they go around really fast. Far away, they go around really slowly, which means their torsion is going to 0. They're becoming straight lines. But if the torsion's going to 0, then it can't have this periodicity. I can always go far enough away where the torsion of the pitch streamlines is smaller than the pitch or the ground state of the smectic. So it turns out you can't take any smectic, you can't take any smectic and decorate it and make it into a cholesteric. You can't make a cholesteric texture that's this. You can have it be not a cholesteric in some places. You can add extra stuff, but you can't take this and decorate it to make it a cholesteric. So cholesterics and smectics are also different. Usually I end with something that's, well, you have to come to the Gordon conference where there'll be an R-rated part here, okay, if you're interested. But this is the group that I worked on with all this, you know, lots of people, and it's been a long, very complicated story that's taken us, I don't know, it's taken us 10 years to get here. I remember the first discussion in 2005 we had about this. Oh, was somebody's not even in the picture, right? And, you know, and now here we are, and we referenced, what's his name too, Yves Boulogon. So thanks for your attention.
Thank you. We have a few questions.
So Randy, you know, in Dejean's book, there's this homework problem that says, you know, show that a cholesteric is a smectic in terms of the fluctuations.
Yeah.
And it cites some work that Tom Lubensky did in his youth, right, of finding a distorted cholesteric configuration and finding that the energy of that is the same as a distorted smectic. So do you have a way of doing that kind of coarse graining within this formalism?
I understand your question. Let me turn your question around. Okay. So that homework problem, I believe it was problem 13 in chapter 7. In that homework problem, they said if you have a cholesteric ground state and you look at fluctuations around it, it's the same as fluctuations around a smectic ground state.
Right.
And that's absolutely true.
Right.
Okay? But that's what I was saying. This is the cholesteric ground state. It would be wrong to use that theory of smectics around a highly distorted smectic structure also. So you're asking, if I give you a distorted smectic and somehow look at fluctuations around the distorted smectic, you might say, suppose I gave you a smectic with all these focal conic domains in it. Could I then talk about a fluctuation theory around the focal conic domains? And the answer is yes, you could. But that would be very complicated. It would depend on the local geometry. And the same thing is true here, right? But I would guess it would be different when you had a complicated texture. Sure, when you have the same ground state, it'll be the same theory. I'll just remind you, smectics don't have cholesterics don't have dislocations. You know that, right?
Kind of.
How can they have a dislocation? They have no translational order, right? A dislocation only can be when you walk around and you think that you know where you are, which floor in the building you're on. But a cholesteric doesn't have floors. It's completely homogeneous, right? So you're going to say, what is it? You're going to ask?
What is it?
It's a chi disclination, right? It's like a chi disclination in a biaxial nematic. You get a winding, the end field rotates around.
It's a parking garage.
No, a Smectic's a parking garage. Cholesteric is not a parking garage, not even for fish.
So, Randy, I have a question. So you nicely presented these three old phases, the biaxial nematics, cholesterics, and smectics.
Mm-hmm.
So why don't you include the twist bend nematics?
Why don't I? Well, I don't know what the right symmetry theory for a twist bend nematic is. If you would ask me, I would say a twist bend nematic is closer to a cholesteric than it is to a smectic or biaxial nematic. But that's, I don't know, we don't know what it is yet. What's the order parameter for the twist bend nematic?
Okay, I think it's time to move on. Thank you very much.
So Randy, what if these tools hadn't been able, did you know going in that these tools were going to be able to differentiate the smectic from the cholesteric?
No, in fact, I have witness. I have witness that 2 years ago in what's that country? England, right? In Cambridge, England, at the Isaac Newton Institute, I came up to you. Do you remember? I came up to you and said, I think we know how to study the topological defects in a smectic by mapping it to a biaxial nematic. I was very excited, right? In fact, we thought we could, right? And we realized that we couldn't because we didn't even understand. We had to go through the cholesteric to get from one to the other. And we realized we didn't understand the cholesteric at all. So even though this is a talk about cholesterics, really the motivation was smectics. Right.
Okay, then now let's go.